Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today we're going to take a question from Martin Christiansen, OZ1KU. Okay? And he has a rather long and complicated question. And running through the question is mistaking circuit theory, which is how electricity behaves in wires and capacitors and inductors and stuff like that, versus RF field theory, which is how RF acts in antennas and transmission lines and hitting the ionosphere and things like that. It turns out that circuit theory is a subset of RF field theory, and it's a specialized subset. And quite a few things that we think of as just being simple numbers like resistance can turn out to be, in reactance form, have phase angles and stuff like that. They can be different. So let's keep that in mind as we look at the question. He says, first of all, thank you so much for all you do for the hobby. My question is about loading coils and antenna efficiency. As soon as you mention loading coil, we're into RF field theory, okay? We're out of circuit theory. So they're going to behave differently from what our intuition might otherwise tell us, okay? So let's get a primary and simple concept out of the way right at the beginning. And that is all antennas that transmit are resonant. Now, they may not look resonant, but something somewhere in the system creates, in addition to the antenna, some other reactance that cancels the reactance in the antenna and adds to the resistance so that you get 50 ohms. This can be done with an antenna tuner, can be done with matching stubs, or you can fiddle with the antenna until you've got it resonant. Some antennas like rhombics, you may think that they're not resonant. They are, but you have to have appropriate tuners to do that, to bring them. Remember, the tuner plus the antenna plus the transmission line as a whole has to be resonant, even though the rhombic itself or the long wire itself or whatever is not resonant, okay? He says, to my knowledge, an antenna only radiates where RF current flows, and the larger the current, the stronger the radiation. Yes and no. Mostly yes. You've got a dipole, okay, and in the center of the dipole, you have the low voltage. And at the ends, you have the high voltage. This is a resonant antenna, high voltage. And here you have high current. And here you have low current. Okay, this, by the way, can be for a dipole, can be thousands of watts, or thousands of volts. The current can be very high. Now, at any given point along here, the impedance is equal to the voltage divided by the current. Okay, voltage equals IR. The impedance is voltage divided by the current. Note that these have phase angles. Okay, so that means that the impedance can have a phase angle too. What we would like at the center is 50 ohms at 0 degrees phase. We're not going to get that. In actual systems, if this is a true dipole, meaning a true half wavelength, this would be more like 37 degrees here. Okay, but the point being that the whole antenna radiates. Okay? Now, there are two ways of shortening an antenna. And I'm going to use a vertical because it's easier to understand. You can do this with the dipole too. However, you end up duplicating it. So let's do a vertical here. A vertical can have a loading coil that adds inductance. If this wire is too short to be resonant, then it will appear to be capacitive. It won't be resonant. So you add a loading coil to make it resonant. The other thing, and this is where it is fed. The other thing that you can do is put, if you have this as your antenna and you attach a metal strap like that, you're adding capacitance. Adding capacitance to an antenna will cause it to appear longer. Capacitance at this end of the antenna will make it appear longer. Okay, and that way you can. And now I notice this is what's happening. This will make it appear longer here. This will make it appear longer here. This is the fed end. This is the non-fed end. What part radiates? You'd say that part radiates, and it does. But the thing is, what we are talking about in RF terms is a system, and this is the whole system here. Okay, and that system will resonate at a certain frequency. And because it is resonant at that frequency, it will radiate. And the current, you have to think of the current in here not as a waveform, but as a, well, if you're CW, steady AC voltage. Everything is RF. It's AC. There's no DC in here. Okay? So if you go too far with the capacitor on the top and too far with the loading coil on the bottom, you can actually get this thing down to a point, and then this and this will resonate together. And the problem is that all of your resistance is going to be ohmic, and nothing will actually be radiated because there is no radiation resistance if it's just pure resonant circuit. So you've got to have some resistance in here. Now you want this resistance to be low. In other words, you can go to thicker wire if you want, something like that. And you will have radiation resistance plus ohmic resistance. The ohmic turns to heat. The RL is radiated. Okay. The way that works is if you collapse this thing to where you've just got the loading coil and the capacitor, your actual resistance in here goes down and approaches zero. Well, that becomes your ohmic resistance and absolutely swamps the radiation resistance. So you'd like it a little bit longer. However, it's quite remarkable how, like shipboard, you can put up like an 18-foot whip and then have a loading coil at the bottom, tune it to any frequency in the HF band you want, and wail away. Of course, you've got a counterpoise there, which is the ship. And the ship is a whale of a good counterpoise, plus it is connected to the ocean, which is an outstanding ground. Okay, so what we want, like for example, if you take a look at one of the MFJ I think they call them antenna sticks. They're divided in half. This is a wire kind of lazily wound around. And then there's a loading coil in the bottom. And then it's lazily wound around to here. And then this is a stinger. And you can put the stinger inside, outside of the end of this thing. And it will be a very nice antenna. Now, this right here, for 80 meters, I put together an MFJ octopus that they sent me and tried it on 80 meters. And what happens is when you put this loading in here, the Q of the circuit goes up. The Q of a reactive circuit, the Q of the reactor circuit, you've got capacitance, inductance, and resistance. And you can measure the Q of the circuit. These two determine the resonant frequency, okay? This one right here determines the ohmic losses. As the resistance goes up, the bandwidth of this circuit goes up. So instead of a real sharp point, you'll get a point that's like this. And if resistance keeps going up, you end up with something like this. It's pretty broad band. Okay, but notice the transformation factor, the Q, goes down as the bandwidth gets narrower. So if you do an 80 meter hamstick, what you get is something that's very high Q. So you do get a lot of current. There's a lot of current in here. Okay, and it radiates really well. This is the principle by which magnetic loop antennas can radiate really well, and so on. But you'll notice that what they trade for being able to radiate really well is bandwidth. They can only transmit really well over a small portion of the bandwidth, okay? But they do work. And if you have this tunable down at the bottom, tune it for any frequency you want. It won't work very well with your pan adapter because the radio can only hear such a short or such a small segment of the antenna. Okay, now I've really deviated. Let's see if we can bring this back to reality. Okay. Now consider a full-size resonant dipole. The current is largest in the middle and the overall ohmic losses are small. Well, the ohmic losses are higher where the current is higher because it's I squared over R that equals the ohmic loss. Okay, so if the R goes down, then the resistance goes down, you lose less power. It's I squared times R, I squared times R, I squared R. And the current can go up because of the Q. It's a resonant device, so there's going to be what are called circulating currents. The circulating currents will go into both the capacitor and the loading coil. Okay, now consider a full-size resonant dipole. Now we make the antenna somewhat shorter while keeping the operating frequency. The antenna is not resonant anymore and its efficiency on the operating frequency drops significantly. True so far. Not because of bad SWR. No, wrong. The SWR is a measure of the power reflected by the whatever it is you're measuring, the antenna plus the feed line. And so you're sending power out to it. It's not radiating the power. It's sending it back to the transmitter. Okay, that's the reflection. Okay, SWR. It's to measure the amount that's reflected. He says not because of BadSWR, which is just a matter of matching. No, there's got to be a place for that reflected power to go. If it will not go back, you either overheat your transmitter, something has got to make that antenna resonant, and it ends up being part of the transmitter that does it. Okay. Less power making the antenna being radiated. The part that is not radiating has lost its heat. No. The part that is missing, suppose you send 100 watts out to an antenna and you get 20 back. All the antenna has to work with is the 80. Part of that will go to ohmic losses, and part of that will go to the radiation resistance. Okay, and then the rest of it actually literally is bounced back to the antenna. Okay, now we wind a proper loading coil and insert it, say at the end of the shortened dipole. No, you want it at the beginning. A shortened dipole is capacitive at the center. And so that's where you want to put the loading coil, and it's inductive out at the end. So you want to put it in the right place. Whole antenna equals the coil and the straight part combined is again resonant. The operating frequency can easily transfer power to it. Well, but take a moment and think about it. The straight part of the antenna is still too short. The antenna system is what is radiating. Okay, it has found a resonance because there is some inductance that has been added to it to make it resonant. Therefore, the antenna effective length is a half wavelength, okay, even though it may appear to be less. Let's take a moment. A straight part of the antenna is still too short, and hence that part must still be as bad a radiator as it was before the coil was introduced. No, not at all. It wasn't resonant before. Now you've added a resonance, so what happens is you send coil down and it gets energy down and it gets to the end and it comes back. Okay, well when it gets to the end it's delayed slightly in the coil and then sent back, and everything lines up perfectly so that it's resonant. This is the whole point of the coil. It changes the timing, the phasing of the energy. It says the straight part of the antenna is still too short. Irrelevant, because it's working with that coil to get things phased properly. How about the coil then? Does the coil itself radiate? Actually, generally not. What is the current distribution across the coil and across the whole combined thing compared to a single full-size dipole? Okay, suppose you've got a loading coil here, okay, and you're end feeding it, doesn't matter. You've got energy that is moving this way at the speed of light in a wire, and then it hits the inductor. The inductor will absorb it and then resend it out. There's a time delay. And then it comes back out here, and because it comes out here, it forms that real nice voltage waveform like this over the part of the antenna that radiates because of the delta T getting the phasing right. Is it a good idea to divide the coil into two halves and insert each half in each end in order to maximize the current in the straight path? It's not going to maximize the current. Think of a reactance as a delay device, or negative delay, which would be leading. Capacitor will lead. It will appear to lead because you put energy into it, and just about as the thing is all the way around, it'll send that energy back. So it appears to lead. The coil is lagging resistance. The coil probably does not radiate. Now, you've got to get away from the idea that the antenna consists of a piece of wire, and by golly, the RF is going to confine itself to that antenna. It does not. Think of a Yagi. You've got two other elements in a three-element Yagi besides the driven element. In the director and reflector, in fact, are entirely parasitic. They're not connected to anything. And they do their magic with parasitic attachment to the driver, okay, or the driven element. And we're doing something simple here too. The fact that something does not look like it is resonant at a certain frequency, it may be, by adding a little inductance or capacitance, may very well be resonant. And being resonant, it's going to act like a dipole. It's going to behave like a dipole and radiate like a dipole. Now, because the current is flowing through the coil, there is I2R losses or resistive losses in the coil itself. Okay, so you like your coil to be hefty. Not some little tiny thing, but something hefty that can handle 100 watts. Now, when you have a resonant device, let me just draw this out here, you're going to get circulating currents. Let's suppose we have a classical tank circuit. Okay, this goes at the frequency, what is it, 1 over 2 pi LC, whatever the frequency is. You get this charged, and then its charge goes over here, and then you get this discharges, while this discharges, this charges, then this discharges, sending the current back over to here, and they will sit there and exchange the current. If there is no resistance here, in other words, if the Q is infinity, it will continue to do this forever, and what you will get out of this will be a sine wave. By the way, this is how oscillators work. You take the output of this, amplify it slightly, and feed it back in phase. Okay, the higher the Q, it will, note that the frequency is not dependent on a resistor in series here. Okay. That will stay the same. This, however, will dissipate heat. And so the Q, which actually stands for a quality factor for a tank circuit, will behave that way a little bit. Let's see. Is it a good idea to divide the coil into two halves and insert each half at each end? No, if you're going to put a loading coil on one end, put a capacitive loading on the other. Seems to me that a coil is simply a matching component. No, as we've seen here, it's part of the frequency determining element, which allows the antenna to be resonant. And being resonant, there are large circulating currents inside there. It's not just something to add to make it the right impedance. It's something that becomes part of the antenna so that the entire thing that's supposed to be an antenna will resonate at the right frequency. So it seems that the part responsible for the actual radiation is still the straight part. Yes, it's the straight part, but the effective length of the straight part can be quite different from the physical length of the straight part. For example, a ham stick can radiate almost as well as a dipole, even though it is substantially shorter because it is loaded and tuned Now what you lose is the bandwidth, because the more you shorten, the more or the less the less resistance there is. Therefore, the higher the Q, therefore, the less bandwidth. As I showed earlier with that diagram when I was showing the high Q versus the low Q. This is the multiplication factor of the Q. Because you take the voltage applied and multiply by the Q to get the total voltage here, and that can lead to some horrendous circulating currents here. And unless you make your oscillator parts out of very strong stuff, you're going to get a lot of I2R losses. I know this sounds a little weird, and some of it is even a bit beyond the extra, but nature works the way nature works. Okay, so there we go. Enough with that. All right, so thank you very much for watching. If you would like to contribute to this channel financially, you certainly may by going to dcasler.com/support. Also, I would like to encourage you to feed the algorithm at YouTube. Think of the algorithm at YouTube as a big voracious bear. It's never satisfied. But please subscribe and like and share. And until we next meet, 73.